Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 20th, 2026, about 5 days ago. It introduces a new architecture called a linear policy net, which, combined with a specific mathematical penalty, eliminates the jittery, unrealistic motions often seen in deep reinforcement learning. The paper is titled, Learning Smooth Time Varying Linear Policies with an Action Jacobian Penalty. And as we'll see later, the resulting motions are not only smoother, but surprisingly robust when deployed on physical hardware. To start off, Figure 1 illustrates the capabilities of this new system. We see a simulated character executing highly dynamic skills, such as the aerial kick in the top row, and the table tennis swing in the bottom row. Typically, deep reinforcement learning struggles to generate such complex motions without unnatural jitter. Yet, as shown here, the linear policy net produces smooth, time-varying behaviors that closely mimic the fluidity of real human movement. So how does the system achieve this performance? Figure 2 details the architecture of the linear policy net. In the top section, a neural network takes a reference state, not the current simulation state, and outputs a feedback matrix, KT, along with a feed-forward term, KT. Then, as the equation at the bottom illustrates, these parameters are applied linearly to the current simulation state to determine the final action. This structure is key because it makes the smoothness penalty, or Jacobian, trivial to compute. Moving on to the results. Table 1 compares the smoothness of policies trained with different methods. The proposed linear policy net, or LPN, appears in the first data column. If we focus on the walking task, and specifically the high-frequency ratio row, the difference is stark. The LPN achieves a score of 0.9, while the unregularized baseline, labeled no reg, is nearly 10 times higher at 8.8. This confirms that the method effectively suppresses jittery, high-frequency signals. Well, having established that the linear policy net produces smoother motions, let's check its learning speed. Figure 3 plots total rewards for 3 tasks: walking, backflipping, and footwork. The blue line tracks the linear policy net. In the middle and right plots, notice how this blue line spikes upward much earlier than the green line, which represents a standard network with the same penalty. This lag occurs because the standard architecture makes the Jacobian penalty computationally heavy and harder to optimize, so the linear policy net isn't just smoother, it converges significantly faster. So Figure 3 showed the efficiency gains, and now Figure 4 illustrates the improvement in signal quality. The top plot displays the ankle action for a backflip, while the bottom tracks a footwork drill. In that bottom graph, notice the green line, which represents the unregularized baseline. It oscillates wildly, creating high-frequency noise that is dangerous for hardware. By contrast, the blue line for the linear policy net is smooth and stable, effectively filtering out that jitter. To conclude, this work shows that we do not need to choose between the flexibility of deep learning and the smoothness of linear control. By structuring the policy to make the Jacobian penalty cheap to compute, the linear policy net generates robust, lifelike motions that transfer well to physical robots. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.